Open any newspaper today, and you will find one of two things: breathless excitement about artificial intelligence solving every problem humanity has ever faced, or warnings about it destroying jobs and civilization. Neither is a useful frame for understanding what is actually happening. Before we examine artificial intelligence, we have to look at natural intelligence. It is a collection of related capabilities: the ability to perceive the world, recognize patterns, adapt to new situations, and apply knowledge across different contexts. When researchers talk about AI, they are talking about the attempt to replicate one or more of those specific capabilities in machines. The goal is to reproduce cognitive functions, like pattern recognition and logical reasoning, not to engineer human consciousness. Because a machine can write a convincing email or beat a grandmaster at chess, it is easy to assume it experiences the world the way humans do, with preferences and feelings. It doesn't. But the ability to execute these cognitive tasks at superhuman speed and scale remains significant. Whether the machine has feelings is secondary to the fact that it can now process information at a scale that was previously impossible. The attempt to build these systems dates back to a workshop at Dartmouth College in the summer of 1956. Researchers like Marvin Minsky convened around the conviction that every feature of intelligence could be simulated by a machine. They predicted human-level AI was a decade away. Early experiments focused on building mechanical systems that could navigate physical or logical rules. Programmers explicitly mapped out knowledge as logical statements and built systems that reasoned by applying those rigid rules to specific situations. This approach, known as Symbolic AI, produced results in narrow, well-defined games. But outside of those isolated domains, the systems were brittle. Every rule had to be manually written by a human. When they encountered real-world complexity, they collapsed, triggering massive funding droughts known as AI winters. This diagram shows how machine learning inverts this process. Instead of a human programmer writing explicit rules to process inputs, you feed the machine thousands of inputs and outputs. The machine analyzes the examples and identifies the rules itself. By learning directly from thousands of examples, computational systems can handle nuance and variation at a scale that no human programmer could manually document. Yet, early machine learning still required a process called feature engineering. Human experts had to manually tell the machine which specific attributes of the data it should pay attention to, directing an image classifier to look for edges or color distributions. The machine could learn the rules, but its potential was capped by a human's ability to first categorize and engineer the raw data. Deep learning eliminated that bottleneck. It is a specific architecture of interconnected computational nodes that learns its own features directly from raw data, without any human guidance. This animation illustrates representation learning. As data passes through these sequential layers, the network automatically learns increasing levels of abstraction. The first layer detects raw edges, the second combines those edges into shapes, and the third combines shapes into recognizable objects. For years, the dominant networks for processing language operated sequentially, one word at a time. They maintained a running summary, but by the time they reached the end of a long paragraph, they had forgotten the beginning.
In 2017, a team at Google published a paper detailing a new architecture designed to bypass this sequential limitation, the transformer. The transformer uses a mechanism called attention. Instead of reading words one by one, it can process all elements simultaneously, analyzing the mathematical relationship between every single piece of data in the sequence at once. This direct mapping allows models to track long-range dependencies across massive documents. A word on page 1 directly influences the interpretation of a word on page 50, moving the system past shallow pattern matching and into contextual comprehension. These architectures also exhibit a unique scaling behavior. Feeding larger transformers more data and computing power yields greater capabilities. That architectural shift is why modern systems cross the threshold from rigid software into fluid, capable language engines. It is crucial to distinguish between narrow AI and artificial general intelligence. Narrow AI systems are capable in isolated domains, like identifying tumors in medical scans. General AI would possess the flexible, adaptable intelligence of a human across all cognitive domains. We do not possess artificial general intelligence. Despite their outputs, modern systems lack persistent desires, common sense reasoning, and true experiential understanding of the physical world. Current large language models are best understood as exceptionally broad, flexible, narrow AI. They can write code, analyze legal documents, and translate languages, all from the exact same underlying model base. The gap between narrow and general AI has shrunk. However, a system does not need to reach human-level general intelligence to change how professionals process information and make decisions. The models driving this shift represent billions of dollars in capital and research deployed by organizations like OpenAI, Anthropic, Google DeepMind, and Microsoft. The physical bottleneck governing this era of development is computational power. Training these massive neural networks requires a constant scramble for specialized hardware, primarily nvidia graphics processing units, housed in data centers running around the clock. Today's systems are actively deployed. They pass professional licensing exams and generate commercial revenue, creating a self-sustaining cycle where revenue funds the research for better models. Knowledge work is defined by gathering information, processing it, finding patterns, and producing insight. Those are the exact cognitive operations these new network architectures are built to execute. As these systems absorb tasks like summarization and data analysis, the human role moves toward higher judgment activities, strategy, ethical reasoning, and managing stakeholder relationships. The technology acts as an economic force multiplier, rewarding individuals and organizations that adapt to overseeing AI workflows rather than performing volume-based information processing. Moving forward, you can safely ignore debates about whether machines possess consciousness. Those questions are not relevant to how you use the models in your daily work. The questions that demand your attention are practical. You must learn the strict limitations of current systems, how to avoid their known failure modes, and how to critically evaluate their outputs. With the historical and structural foundation laid, the next step is applying this understanding to the systems in front of you. We are moving directly into the mechanics of generative AI.